So last lecture I described the fundamental axioms of quantum mechanics. Okay. These are again the axioms with respect to the non-relativistic formulation of quantum mechanics. When you include relativity, things get modified. And we know that relativity is definitely there. There is a combination of quantum mechanics with spatial relativity, which is known as quantum field theory. There everything works fine. There are no contradictions of any types in quantum field theory. But if you want to do that, you have to go beyond what these axioms which I listed last time. And for most of our purpose of quantum communication, the axioms which I have listed are fine because the hardware is all going to be non-relativistic. But yes, you can ask, what about photons? There is no way to describe photons without invoking relativity. They move at the speed of light. So yes, we have to be a little careful when dealing with photons, but that also can be included in the same non-relativistic framework without too much trouble, and so we will live with that. Quantum field theory is a different story, and then all the things which I said, starting from the definition of the states themselves, they get modified, and you have to work in a different space, not the Hilbert space, but something which is called a Fock space. But all those details can be ignored for the purpose of this whole course. So, last time I described these axioms, but in a basis independent manner. So you didn't have to specify any basis, you only have to write down what are states, what are operators, etc. But it is much more convenient for practical purposes to work with a particular basis. Okay, it's in some sense convenience because you can write down things much more explicitly, and I will do that today for the same set of axioms which I described last time. But I will emphasize again that basis is a choice of convenience or convention. It is not necessary for describing the fundamental principles. So the first thing which I defined last time was states. So we will choose a basis in the Hilbert space, which I will again all the usual things. It's an orthonormal set of vectors, essentially similar to Cartesian coordinates. So vector space, I can always do that. So then I can write this state which I was denoting by this symbol psi as a vector. I can explicitly write it down as some coordinates and some vectors which denote the various directions, and sum of everything with the normalization convention is that, or rather much more precisely, they are orthogonal and unit magnitude. I have to define this dot product itself. but these are CIs are all numbers. In general, it's a Hilbert space is a complex Hilbert space, so they are complex numbers. So what is the structure which is required in Hilbert space? That in addition to writing the component, I should be able to define the dot product or the inner product. Okay. So how does that work? So okay. I just put the label explicitly. One of them will be C and another will be D in the expansion coefficients. So this is constructed with this orthonormal convention as product of individual components summed over all the possibilities, and because it is complex, this cat vector, no, cat is this is called bra. Okay, so the bra vector gets conjugated, the cat vector remains whatever its value is, and this is a general dot product, this is a particular case. Okay. Now there are extra conditions which we will impose, which is that the state is normalized. What is this quantity? It is by this definition mod C square that becomes equal to 1. This is a generalization of the Pythagoras relation, nothing more than that. Then what I need, yes, how many parameters are there in defining these numbers? Well, in the n-dimensional space, there will be n of these complex numbers, but there are constraints. So one of the constraints is this, that they are not all independent, the sum square is equal to 1. The other constraint which I mentioned, that the overall phase of the state is not observable. So because of that, the number of independent components are two n minus 2. Remove, and 2n is just n complex numbers, and so these two are subtracted out. They cannot be observed in a physical situation. So these are the number of degrees of freedom which are free and available. So this is for describing one particular state. Okay. We need a convention for combining multiple states, okay, just like letters in a word. Okay. And that convention is known as a tensor product. Which combines states as ordered sequence. the order is important in any convention of our whatever one-dimensional sequence which you look at. Change the order, the meaning can change. And this is called product because the number of dimensions of individual states or whatever components, they multiply in this particular process. Very similar to what we have in any of our one-dimensional languages. How many possibilities are there for the first one, how many for the second, etc. The total number of possibilities is the product. That is why it is called a tensor product. Okay. So we have to pick a convention for the order, and we will pick the same convention which we use in our number system. Okay. So for example, let me write the same if I want to do this, what does it look like? So it will be represented, I have to write a vector notation for everything as well. So, okay, do that as well here. So this is one way of writing the vector. The other way of writing is just explicitly list all of them numbers, something like that. So this becomes equal to again I should use the mapping, so it's the two dimensionalities do not have to be equal. So how do we write this thing as a big array where as I said, we are following the same convention as we use in the number system. If I look at two-digit numbers, I will start with 10. The first digit is fixed, goes from 0 to 9. Then the second digit will become 2. It will go from 0 to 9, etc., etc. Okay. So this is an explicit result for tensor product. You can do it with states, but you can also do it with matrices, which will, well, the next step, but I will write down the result anyway. But suppose I want to perform a tensor product of two matrices. What do I do? Construct is a similar structure. Well, I will write A11 and then the whole matrix B, whatever it is. Then A12 and then the whole matrix B, A21, then the whole matrix B, etc. It's a convention, it defines the order in the sequence, and we have to follow it to be mathematically systematic. And a lot of stuff then will follow from this tensor product structure for many properties. Yeah. Yeah, so this will be the whole matrix. A11, this again the two matrices don't have to be same dimension, but if it is say I will use only n by n and this is m by m, then this structure will become n m times n. So there will be n of these, and every one will vary m indices in each one of them. Yeah, A11 times B is a matrix itself. Okay. Okay, so this is the structure we'll need for explicitly writing down all the states. The next thing which I yes. They are different Hilbert spaces. The dimensions are different. Yeah, it's out of product, not out of product, but it's a tensor product. Out of product will come with a little different meaning. Okay. So again, I will start with one operator, and they will combine by this rule when you go to a higher space with larger number of components. So the observables are Hermitian matrices, and for any Hermitian matrix you can prove that it can be diagonalized by a unitary transformation, and all the eigenvectors are orthonormal. You can choose them. So that I am going to leave it as an exercise for you to work out a little bit of linear algebra, but this is always possible, and so I will assume that the eigenbasis can be constructed just like this Hilbert space basis. So this will be denoted, let me put a little bit different notation. Again, orthonormal, and these eigenvalues are in case of Hermitian matrices, they are real. So these properties allow us to write any operator as the weight, which will be the eigenvalue, and this is the object which is called the outer product. It is just a matrix. So, let me again write a convention, but it is always outer product, the dimensions of these two things are the same. It's in the same Hilbert space, and if I want to write say EI, not EI, just any arbitrary combination is fine. And if I want to describe this particular outer product, it is a matrix, but it will be a square matrix. And its components will be C1 I star by given these two values, where I and j are the matrix indices of the things, and the values will be complex conjugate of, or the other way around. This one is complex. And this one is unconjugated. This is again a convention that which one is bra and which one is cat, that defines what is complex conjugated or not. And this is just a product of number. It will be a array, and I and j are the matrix indices. So this combination actually is a diagonal combination. Okay, this is for arbitrary I and j, but here the indices are the same. So this is diagonal and if I want to write it because I choose this basis to be orthonormals, I go to that coordinates and only those values where the index is 1, 1, it will appear here. If it is 2, 2, it will appear here, things like that. So this is the general outer product. And this is written down, or rather it comes from solving this diagonalization problem exactly, because we can immediately calculate what is O acting on EI, because this is normalized. If I multiply those things, EI will become equal to 1. And so this just gives lambda I EI, because of the convention. And this is exactly the eigenvalue equation. So that's how we constructed this notation to automatically define that these are observables, these are the eigenvalues, and this is the eigenvalue equation. That is what we solve to actually go there, but you can do it in many ways, and if you want to write it in a matrix form, it's kind of straightforward. So these are all the operators. There are matrix notations which we can construct, and yeah, how many parameters are there? The matrix is Hermitian. Okay. Hermitian doesn't mean real, but it says that the conjugate transpose is equal to itself. So if you just write n by n matrix, there will be n square numbers. But the condition that the conjugate transpose is equal to itself removes half the constraints. Okay. So if you want to make it more explicit, n numbers which are on the diagonal, they have to be real, because the transpose doesn't do anything on the diagonal, it's equal to its conjugate, and the off diagonal I have to count only on one side and the other side is automatically determined. So that number is n minus 1 by 2 is the number of off diagonal components, but they are in general complex. Okay. So this is off diagonal. And this number is just n square. If you want to list it explicitly, these are the number of degrees of freedom you have to keep track of. Because in a particular situation, you can simplify like this expression, but then you can ask where are all the parameters gone? The parameters are gone in defining these eigenvectors, how they are pointing in the whole space. This fact actually also holds for unitative matrices for a trivial reason. Because u equal to exponential of a Hermitian matrix, and that also has the same number of parameters. How you choose is your convention, but that other trivial relation. So whatever you need to describe h, you can describe the u using the same convention. Okay. So this is as much as I can fill in for all the operators, and the next thing which I described was a measurement. This, as I said, is a irreversible process, and we are taking it as a postulate, okay, forgetting about how that will actually happen, which is at the moment still an unsolved problem. But measurement involves both these things, that there is a state and you measure some particular operator. And what happens, therefore, depends also on both of them. So, So we have psi which can be written as this, we have O which can be written as that. And the prescription is that it's the overlap of the state with the corresponding eigenvector of the operator, which gives you this result, and this thing is referred to as Born rule. There are different ways of writing this quantity, and one way is to just evaluate this kind of product. Okay. These are the two Bryan-Ket vectors. This is a matrix in the middle. So now let us plug in all the quantities explicitly. So I have inserted this expression for the operator, which is this. The order of lambda I where you put in doesn't matter, this as long as the order of these vectors is maintained. So I just put that thing in the middle. And so this is this particular combination with a weight which is equal to the eigenvalue. And in probability theory, this is called the expectation value. You have various values with some probabilities. And what is the average? Well, this is the average. And it has a abbreviated notation where you don't bother to write this psi and psi, but this is the so-called expectation value. This is not the whole story. There is something else which happens, which is the projection. So after measurement, it is a kind of branching process. So many different branches with different probabilities, but in each branch the state becomes the corresponding eigenvector. And this is a peculiar behavior. It is not any of those other processes which are deterministic. Okay. So this is inherently it is probabilistic. So I will just write that other processes in the quantum mechanics are deterministic, but this one is not. So measurement is something peculiar, and we have to keep in mind. Most of the time in dealing with quantum computation, what you do is you start with the initial state, you apply a whole lot of transformations and perform measurement only at the end. So in that strategy, the whole evolution going from the input to the final state is deterministic, and when you measure the final state, it becomes a probabilistic result. But that is a general stating which we use, and it is well connected with this axiom of what happens during measurement.
One question, what do you mean by branches approach?
It's a probabilistic process. So what happens, there are multiple options. I'm calling them branches because they all came from some common initial point. Yeah.
Why any observer collapses to the any of either vectors by measurement?
That is the dynamics of the measurement, that the result will be one of the eigenvectors of the operator that you measured. Do not get anything else. And that is based on experimental observation. And the last stuff which I defined is the evolution, which is the whatever happens in between, and which was defined by this equation in general. All these quantities psi and h and this one, they are all time dependent. So this is
Sir, when we calculate this expectation value, this is the expectation value of a state.
of a corresponding observable in a particular state. Both are there. Yeah.
So when we go from an initial state to a final state,
Yes.
there will be a number of intermediate states.
The expectation values change. They
We
change.
will be measuring these every intermediate state.
You do not have to measure it. You can calculate, but you do not have to measure it. Measurement is generally reserved till the end of the process.
Even if we measure for each intermediate state, it will be the same.
Yes, it will be different, and but if you try measurement, this irreversible step will enter at that particular stage,
The information will be gone.
and then the information is lost. So, for example, what happens when the state you start with a this CI initial one, that particular component will survive, but or the component along EI will survive. All the other ones which are there in the state, they all are lost. So if I want to write that when I say this, all these components are lost. And that is a irreversible process. So in this equation there is a trivial solution. As I said, we can do a infinitesimal time evolution. This H is Hermitian, implies that psi final is equal to where u is unitary. I mentioned last time that this Hamiltonian can be time dependent, and then what you do is integrate this for individual tiny steps delta t. We are assuming H is Hermitian, will basically make it more explicit that it is mathematically chosen to be piecewise continuous, but it is bounded, it does not blow up. As long as it is piecewise continuous, I can integrate it for small steps, and every small steps I can do this. So I can write it more explicitly that psi at some t is can be written as u1. I give it a little argument, it's better. I have to write an order, so let me write it in a initial point first and final point second. So it's 0 to delta t, then delta t to 2 delta t, all the way to t minus delta t to t. You can break it up into individual parts, and what matters is whatever it's a time ordered construction, and we will use it in this particular sense all the time by assigning these individual steps to logic gates. Okay, we will never have to the computation is organized in this manner. By definition, you start with some initial state, you apply some gate, and apply all the second gate, apply third gate, etc., till you reach a final step. And each logic gate will be a unitary operator of this type in quantum theory. So And this basically explicitly gives us the framework of what we are going to do in computation. Start with some initial state, apply a sequence of logic operation, you will get some final state, that you perform a measurement and read the result. Okay. And the way it differs from the classical computation is that all these logic gates which are appearing here are unitary evolution steps. In classical computation, that is not true. You can have some operations even in a classical computer which are unitary, there is no problem with this, but here all operations are unitary. That is not true in classical computation. On the other hand, it is still true that whatever you can do with classical computation, even including non-unitary operations, can be done in this quantum framework by including only unitary operations. And that's why you don't worry about that something which is possible in classical computer, can I do it or not? Well, everything is possible. It's fine. Okay. And so I will write down a map this whole framework is there, but I need to compare with the classical physics, and that is done by saying that the classical states are mapped to the basis vectors. Only. So these are n distinct possibilities and no superposition. So here I wrote down an expression, what is a general quantum state, which is some coefficients time I. What is the classical system? It is a subset where there are only n points. All the Ci which are superposition coefficients are not there. So there it is n-dimensional Hilbert space. Here these are just n distinct points. On the other hand, we can associate these n distinct points with the n possibilities in the measurement. Okay. So measurement reduces quantum state to the classical subset. And that has to be true because measurement is something which is going to appear in our instrument some value. and those are distinct values. There is nothing what you call probabilistic about it. It's one or the other, some n distinct values, and we can label them as a classical result. So in some sense, whatever is happening here is you're reducing a quantum state to a classical basis. What that basis is depends on the operator, because these EIs were the eigenvalues of the operator, but that is phrased in another way, that it or it's actually the operator O this label is used. That what classical subset you obtain, it's decided by the operator and its eigenvector, and that is somehow labeled as a preferred basis. You choose a different operator, you will end up with a different preferred basis. And that is a convention, explanation of this label in some ways or the other. But then there is another question which remains, that there is a classical world which we deal with routinely on our macroscopic scale, and there is this quantum world which typically is for describing atoms and molecules. Is there a dividing line? And the answer is no. Not only nobody has been able to find a dividing line, but there are explicit models where you can continuously go from one to the other. And then the question is what do you mean by classical and what do you mean by quantum is in some sense depends on the problem you are looking at. So there are and the most common of these possibilities is harmonic oscillator. You know how to solve it in the classical equation, you know how to solve it in the quantum equation, and you can take one and change some parameters all the way to go from one side to the other. The meaning of what we call the classical state actually changes when you try to do that, and that will be described in probably the course on optics or measurement much more explicitly, but I will just give you a name. If you don't understand it, it's okay. You will learn it somewhere else. But when talking about these things, it appears. So when I say it is a smoothly or continuously connected, what is that you get at the end? And that is a something which is called a coherent state. And there is a explicit parameter which still has to appear to separate the classical and the quantum region, and we know what that parameter is. It's a fundamental constant of quantum theory. It is Planck's constant. And the dividing line is actually not any transition or a discontinuity or any of these things, but magnitude of certain quantity as a compared to the magnitude of the Planck's constant. Okay. So, where this object is buried, and the notation which I have used all over the place, I have not written the time constant explicitly, but it is in some sense in the dynamical equation here, that if you look at the physics textbook, they will put a little bit of h cross inside it. Okay, so then whatever is happening in the scale of the Hamiltonian is somehow related to this scale of the Planck's constant, and that describes the evolution. So there is a quantity which is called action. And it's essentially this particular integral. So because you write down the formal solution, it will be exponential of h dt, but if you put an h cross over here, that integral will be measured by dividing this object with h cross. And this object has a formal name which is called the action, and it has the same units as this object, and we can write down an explicit criteria. If this object, whatever it is, if it is small or comparable to the Planck's constant, then the corresponding evolution is quantum. If it is much larger, the system behaves classically. And so when you literally try to design all the gates, etc., the exponent of the u, which is nothing but this object, you have to make sure that in the hardware, when you put in all the numbers, the quantity is comparable to the Planck's constant. If it becomes much larger, you will not see quantum effect at all, even when you try to construct with this Hamiltonian. So yeah, so many of these points are maybe empirical or just giving you a concept of what is going on. They can be made mathematically more precise, but I am not going to do that right now. But it gives an idea about what is quantum, classical, how you can connect the two, and roughly what is the map between the various variables and components which are involved. Okay. My time is kind of up. Yeah. There is a particular representation which I wanted to point out with this, which is something called a Bloch sphere. I will say more about it probably in the next class, but it is something which is heavily used for two-dimensional states which are called qubits. I had introduced it in the context of just defining the complex algebra and group theory, etc. But I can also write it in this component language. So there will be two states which will denote by this two component vectors, nothing complicated, that is fine. But then I gave a representation for a two-dimensional components where this psi general one was, I think this is what I wrote down. Maybe I wrote down something little bit differently in this notation, but one of the component is cosine theta by 2, the other with a sine theta by 2. There was e raised to I phi for this, and there was a global phase which I don't worry about. So now, what does this represent? As I said, this theta and phi are chosen, so the ranges correspond to the polar coordinates on a sphere in 3 dimensions. But I put deliberately these half angles, and that is to just make sure that theta goes from 0 to pi and covers the whole system, but it introduces a little bit of a caveat which is worth understanding. So now I write what are the various states. Okay. So when do I get the state 0? Is when this term is absent, that is at theta equal to 0, which I can say is the north pole. So the 0 is sitting here. When do I get this state, which is when this term is equal to 0? And that happens to when theta is equal to pi, which is south pole. So, this state in the usual sense are orthogonal, but on this coordinate notation they are diametrically opposite. And this is something which is true for this picture for any vector, that if I take say some point with, well, I will have to draw some better figure next time, that I choose some great circle going from 0 to 1 and I put some angle here which is theta, and for the angle phi I have to draw the other axis. So, when I do a projection, I get this angle which is called phi. This is the x axis, this is the y axis, and then this is the z axis. So, now let me look at the diametrically opposite point to wherever this will be. I can't draw it that nicely, but it will be some point diametrically opposite to this, and the geometry tells me now what is the mapping, that if this is theta and phi, what is the diametrically opposite point, and that is going to be the orthogonal combination. So, I am using this notation, but geometry tells me that to go to the diametrically opposite point, I get to change the theta to pi minus theta, and the phi goes halfway around. So, it will become pi plus phi to go from this side to the other side of the relation. And so, if this one is mapped to this object, what happens to this? So, this becomes a state, and I have to evaluate after this substitution whatever it is. So, half of these angles, it will give you cosine of pi by 2 minus theta by 2, which is sin theta by 2. Phi is going to go from e raised to I phi to e raised to I pi times e raised to I phi, and e raised to I pi is minus 1. And sin theta by 2 again is pi by 2 minus theta 2 becomes cos theta by 2. And now you can immediately see what is the dot product of this with that. It's 0. Which means diametrically opposite states are orthogonal. So, it looks little bit different than our normal vector coordinates, where you want to make orthogonal, you make it 90 degrees. Here it is 180 degrees. But that is all because of this sticking in this half angle over there. But it is a convention and you have to get used to it. So you will represent the state on the sphere by some point theta and phi. The diametrically opposite point is orthogonal to it. And then you can ask what can you do by applying this unitary transformation to change theta phi from one value to another value which will correspond to some logic gate. So that kind of description I will give you next time. Okay, I will stop at this particular stage. Yeah. Yeah.
So like you multiply it with e to the I phi because you consider it like an Argand plane, so you rotate it by multiplying the number. I mean, when you want to represent its coordinate on the xy plane, like you take a coordinate.
This is not any dynamics. This is just geometry of the various points on the Bloch sphere.
When you want to like triangulate the point, like you mentioned the polar angle, then the azimuth angle. So for that you multiply it with e to the I phi. So is it because you consider it to be like a Argand plane where you multiply with e to the I phi and then rotates it by triangle phi? Is that what you do?
I am not able to understand your question.
No, I'm asking why is it in that format? Like cos.
Why did I choose this?
No, the second circle.
This.
After the
e raised to I phi, why there is phi angle? The question is why.
is that because
Because it was here. This is a mapping. How do I find a diametrically opposite point to this?
no, I understand that. The way you write the coordinate of a point,
Yes.
the second term after the plus sign, the second term.
In the first equation,
Yes, yes.
Yeah.
Why you have this e to the I phi?
Yes.
So I'm asking why do you multiply that term? Is it because you consider rotation by angle phi along the xy plane?
This was the most general parametrization of a two-component complex vector. Two magnitudes, cosine theta by and psi by 2, which are always positive, and two phases, out of which one phase I can factor out and the other one left over there. Two magnitudes which are always positive, and two phases which are full ranges from 0 to 2 pi. This is the most general parameterization of two complex numbers. That is done before you go on to the geometrical interpretation. The ranges of theta and phi are chosen by particular convention so that it maps onto this sphere.